The preparation of desired organic compound from a readily available starting material is known as organic synthesis. Then singular form of this is SIS, actually synthesis stands for singular, and SES, synthesis, is plural. So suppose the preparation of the desired organic compound, the compound we wish to prepare is called target molecule. So in case of retrosynthesis, generally we will come across with this terminology, target molecule. That is the compound we wish to prepare. So we wish to prepare the compound, generally we will call it as a target molecule, or desired organic compound denoted by TM. TM stands for target molecule in the concept of retrosynthesis. So starting material, so the certain criteria needs to be fulfilled in order to choose as a starting material. The first one is it should be readily available. Just to perform an organic synthesis, you are not supposed to go for the any other highly expensive starting material. Instead, try to search for the readily available starting material in order to get a desired product. The first step is readily available, then commercially availability of those starting material. We need to look into that. Then inexpensive. So the preference needs to be given to the less expensive starting materials over the highly expensive starting material, and contains some 5 carbon atoms or less apart from the aromatic ring. So the starting material generally needs to have a 5 carbon atoms or less apart from the aromatic ring. Apart from aromatic ring, the 5 carbons atoms needs to be present over the aromatic rings, or less than 5 carbon atoms. Such starting material only you need to choose it. So if any of these criteria are fulfilled, then you can choose those materials as a starting material in order to get a desired product. First is readily available, then commercial availability, inexpensive, then contains 5 carbon atoms or less apart from the aromatic ring. Like generally, the aromatic like benzene you have chosen for the conversion of benzene to nitrobenzene. So that is consist of only aromatic ring. And suppose if your aim is to prepare propyl bromide, then you will be taking generally one propene, that is having less than 5 carbon atoms, or else subjectives. The first objective is to get a pure sample of the desired organic compound. So your aim is to get a pure sample of the desired organic compound. The desired organic compound is generally TM, target molecules. Second is to avoid the reactions that will produce a mixture of products. So you need to keep it in mind during the reaction, the mixture of product formation, if it is happening, then you need to avoid those kind of reactions, because those reactions generally gives a mixture of products, and it can be of major and minor product. That those kind of reactions may not be unsuitable reactions. So your aim is to have a single or major products with less percent, like 10% or 5% of the other impurities or the side products. So why you need to have a pure compound then? So in the previous slide, so it is pure compound is required, right? So you need to avoid the mixture of products. So why you need to have a pure compound? To study the physical properties. Suppose if you have a pure compound of the desired compound, then you can do the physical properties. Then comes is you can check its chemical properties. Then pharmacological properties like medicinal chemistry usage, you can do it over the pure compound. So to fulfill this, like physical properties, you can examine over the pure compound. Then chemical properties of the pure compounds can be examined. Pharmacological properties of these pure compounds can be analyzed. That's why you need to have a pure compound. Then reasons for synthesizing the organic compound. Why you need to synthesize organic compound? That is the question. So one is proof of structure of a natural compound. If your aim is to prove that okay, these are all the natural compounds which is present in the nature, then you need to synthesize organic compound. Uh, then to prepare compounds that are useful to mankind, like pharmaceutical purpose, then polymers, dyes, etc. So the aim is to target these pharmaceutical sectors, polymers and dyes. These are has wide applications. That's why you need to perform this synthesis of organic compound. And third point is to prepare specific compounds to study reaction mechanism or biological metabolism, like labeled compounds. So another reason is to understand the reaction mechanism, like what type of reaction it is taking place. So how usually this reaction is forming. So the during the reaction, what and all the intermediates, the reaction intermediates is forming, and whether the formed intermediate is stable. All these things you can study during the reaction. And biological metabolism. So you can also examine the biological metabolism, like example labeled compounds. Then for the intellectual challenges, For the intellectual challenges, new problems demand new solution and can lead to the development of new chemistry, reagents, etc. In order to fulfill this, you need to prepare a organic compounds. So synthesis of organic compound is required. Suppose if you want to develop a new chemistry or new reagents if you want to produce, then you need to perform this organic synthesis. So some fascinating compounds like this or this kind of structure, this kind of structure, or like this, and any of this. So this looks to be very complex, but if you cleave the particular bond systems, then ultimately you need to end up with a small systems like starting materials that should be simple, readily available, and inexpensive, and you can reconstruct these target molecules with the help of well-known named reactions. So we can call it as this as a target molecule, or any of these can access a target molecule. Then question is how to synthesize. So the structure looks to be very complex, but if you do the proper disconnection of the bonds in a proper way, then ultimately you will end up with a simple starting material. So with the help of simple starting material, you can reconstruct these target molecules with well-known named reactions and reaction conditions and the availability of catalyst. Okay, so just to brush up the bond polarity, polar covalent bond, the most heteroatom are more electronegative than carbon, that is oxygen, nitrogen, then bromine, then Cl. So O and B are Cl or electronegative than the carbon. Partial positive charge appears on the carbon as it is an electropositive compared to the neighboring counterparts. But if you have this Si, Mg and Li or electropositive compared with the carbon, suppose if you have a C-Si bond, C and Si bond, then generally carbon is electronegative. Here it is delta negative, and this will act as a delta positive. Similarly, if you have a CMG bond, then the carbon carries same electronegativity. So, and the Mg carries electropositive. In case of CLI, the carbon carries same electronegative and Li carries same electropositive. So, delta negative is over on the carbon, and lithium will carry a delta positive charge. The polarity in the case is reversed. In this case, like carbon Si or carbon Mg or carbon Li bond, so the polarity is reversed compared to the previous slide. So in this case, carbon oxygen bond, if you're looking, then carbon is electropositive, oxygen carries a electronegative. So delta negative charge is on the oxygen. And suppose if you have a CN bond, then delta negative is on the nitrogen, and Br will carry a negative charge, and Cl will also carry a negative charge, and the carbon will carry a partial positive charge. So partial negative charge appears in the carbon in case of carbon and Si, or carbon and Mg, or carbon and Li bonds. Coming to the arrow notation, simple reaction arrow. Do you remember how do you represent this simple reaction arrow? So this is the arrow generally used for the simple reaction purpose. What it says is, suppose if you are using this arrow notation, then reacts to give, like A, then if you put this arrow, gives B. So that means A and B are, suppose if you are taking A converts, or if suppose if you are taking A plus B and it gives C, then in such cases, A plus B gives C. So A and B reacts to give. So this notation, arrow notation, states that reacts to give. And delocalization arrow, how do you represent delocalization arrow? So this is the delocalization arrow. Both the end, you will be having this closed-headed arrows. What it says, two different ways to draw the same delocalized structure. The two different ways to draw the same delocalized structures. That is something about delocalization arrow. Then equilibrium arrow. So this is the arrow notation, equilibrium arrow. The definition of this equilibrium arrow is two structures are interconverting. And similarly, curved arrow, this is the one, curved arrow. The motion of two electrons, suppose during the mechanism, if you want to show the motion of two electrons, then you need to use this kind of notation. Then fish hook arrow, so half-headed arrow, what it represents, the motion of one electron. Then retrosynthesis arrow, so these notations has been already used. Then what type of notation needs to be used if you are saying that the retrosynthesis arrow? Then this notation, this particular notation is for retrosynthesis. So retrosynthesis means backward approach from the target molecules to in order to get a simple starting material. During the retrosynthesis, you need to show these kind of notations only. So two lines, then one arrow. This stands for this kind of notation could be made from. So not in reality. So it is actually a visualization of the cleavage of particular systems. By using this cleaved systems, you can reconstruct the target molecule. That's why you can do the retrosynthesis is in a visualization approach, cleavage of certain particular bonds. That's why this notation stands for could be made from. So now coming to the retrosynthesis, what is retrosynthesis? It is a reverse of the synthetic steps. So you know that benzene, upon treatment with nitrating mixture, you will get nitrobenzene. But suppose reverse step is what? benzene, then HNO3, H2SO4. You will get NO2. So far you know that how to convert this benzene to nitrobenzene. But let us assume you don't know the reaction conditions HNO3 H2SO4. This is actually an synthesis process, general synthesis process wherein benzene can be converted into nitrobenzene. But suppose during the retrosynthesis approach, we will take this as a target molecule. Now let us assume this is the target molecule. Then you need to take the target molecule NO2. For retrosynthesis representation, you need to use this retrosynthesis notation. Now the question comes is where you can do the disconnection or cleavage of bond. So here is carbon and nitrogen. So you can do the disconnection here, right? So you will get two types of synthetic synthons. Synthons are positive and negatively charged species. Suppose one possibility is this carbon can carry a positive charge. Along with that, another possibility is NO2 minus. So here carbon may carry a positive charge and this NO2 minus can act as a synthons, or another way saying benzene, this carbon may carry a negative negative charge, then along with that NO2 plus. So during the disconnection, we can call it as a carbon and nitrogen. So that's why we will generally represent like this CN disconnection, DIX. In this case also, we are disconnecting CN only, bond C and N. So CN disconnection. There are two types of way you can disconnect this CN bond through CN disconnection. One is you may get this particular carbon may carry a positive charge and nitrogen, nitronium, NO2 minus. And another way is CN, wherein this carbon may carry a negative charge and NO2 plus. So the question is, which system can be used in order to get a starting material? Whether the first one or second one. During the synthesis, which is the reaction intermediate?
So do the second one,
Which one?
first one,
First
because
one.
nitrogen being more electronegative than carbon, which is
Ah,
maintaining the negative side.
okay. So I said this is synthons. Can we get any suitable starting material for this? Or for this, can we use any starting material wherein this NO2 minus can be formed during the reaction, or like a benzene cation? There are two ways, but only one fragmentation pattern is invalid. This is actually, you may not get the suitable synthetic equivalents for these two species, but one can get an synthetic equivalents for this because for the synthetic equivalent for this is, you know, that benzene, just protonation of this, one can get the benzene. And for the nitronium ion generation, you need to use the HNO3 and H2SO4. The nitronium ion is the reaction intermediate. So that's why